Добрый день. Я начну лекцию. Добрый день. Я начну лекцию. In the last class, we proved the following theorem about least decodability of arbitrary codes. So this is the statement of the theorem. Assume that we are given a code with block length n, dimension u, and actually the block length, the dimension can be arbitrary, so let's fix it some dimension k. And the minimum distance, which we denote by n minus u. And then this code is decodable from n minus square root of nu errors with least size of linear size to n plus 1. And this is a purely combinatorial statement. So it means that whatever function, whatever string of n characters we choose, the number of code words in our code that coincide with that string in at least square root of nu positions is at most to n plus 1. And the assumption is that any two code words coincide in at most u positions. And let's see what does it mean for Reed-Solomon code. For Reed-Solomon code, we obtain the following corollary. Recall that Reed-Solomon codes are codes in which messages are polynomials of certain degree, say at most k. Then the dimension is k plus 1, and the distance is n minus k, assuming that the block length is k. And the corollary is that Reed-Solomon code with these parameters is, so we have the number of errors we can correct is n minus square root of nk then, and the list size is linear, 2n plus 1, least decodable. And now we will prove an effective version of this corollary. We will prove that actually we can correct about that many errors with a list of linear size in polynomial time. So I will state the theorem a little bit in a vague form, and from the proof it will be seen how vague is, how close what I'm right is to the correct formulation. So the theorem that there is a polynomial time algorithm to approximately n minus square root of n k, and here we write approximately n times n over k, least decode, Reed-Solomon n k plus 1 n minus k cold. So these proximal inequalities will hold up to plus minus 1. And n over k is usually chosen to be some constant from Solomon code. So that means that the size of the list is still linear, assuming that n over k is bounded from above by a constant. And so today in this class, I will just prove this lecture and nothing else will be explained. So more or less that algorithm generalizes the algorithm to decode from errors with list size 1. So just generalize algorithm for normal decoding of Reed-Solomon. So let's recall how it was done. So for normal decoding, in normal decoding, we want to recover a message, P of x, which is a polynomial of degree at most k, as it is. So this is our message. And we are given an input. Our input is not the message, but its corrupted version. That means that we are given the values of that polynomial in n points, different points, and tilde means that some of them are incorrect. So, and we know that the number of incorrect values is at most some value, more precisely, half of the distance. In other words, we know that the number of correct values is large enough. We proceed as follows. Given that input, we find the first step. We find two polynomials. We have denoted them by q and r, such that q times x, q of xi times this corrupted value on xi is equal to r of xi. In all our points and points. And there were other restrictions on q and r. First one is that q is non-zero polynomial. And the second one is that the degrees of q and r are small. So the degree of q is at most e, the number of errors we want to correct. And the degree of r is at most strictly less, but to say e plus the degree of p, and the degree of p is k. Actually, at most, not this much. Okay, and this polynomial was found just by solving a system of linear homogeneous equations, and then on step 2, we just divided r by q, or we show that r is divisible by q, and that the ratio of them is necessarily equal to p. So in the second step, we just found r of x divided by q of x. Now we will generalize these two steps in the following way. First of all, we will understand what does it mean. We will sort of glue Q and R to one polynomial. So we can consider actually the following polynomial of two variables, y and x, which is equal to y times q minus r. So q and r are polynomials of x, and so we obtain a polynomial of two variables, x and y. And this property means that all the pairs of the type xi, p of xi, are roots of that polynomial. So any such pair is a root of t. So the first step may be understood that we find a polynomial of two variables such that every point on the graph of the function tilde p is a root of that polynomial, and with some restriction on the degree. First of all, in y, this is a linear polynomial, and also there are some restrictions in the degree in the variable x too. And this was for normal decoding. And then we divided, we somehow extracted from this polynomial the desired polynomial, our message. And now we will generalize this idea. Instead of finding a polynomial of two variables such that all these points are roots of that polynomial, we will find a polynomial whose degree in y might be larger than 1, but still we will have some upper bound of the degree both in y and x. And also, not only all those points in the graph of tilde p will be the roots. They will be the roots with very large multiplicity. And to realize this plan, so let's write first this plan, the entire plan, and then I will specify what exactly we do. So the plan is find the step 1, find r of xy of small degree, whatever it means, because we have now two variables. So we need to specify how small is degree both in y and such that all pairs xi tilde xi, recall that tilde p of tilde xi is the value the corrupted value we receive from the channel. All these pairs are roots of R of large multiplicity. That's now important. And how large is it, we will have to specify. And on step 2, we will first prove that R is divisible, any such R. I mean, there are many actually, there might be many such R's. And on step 2, we'll prove that any such R is divisible by the polynomial y minus p of x, where p is the message, the salt message we want to recover. And then we will just factor R in the irreducible factors So there are efficient algorithms to do that. So find. So the algebra teaches us that every polynomial can be in a unique way to represented as a product of reducible polynomials. So we will find such a factorization. Find the factorization of R into reducible polynomial. Monomers, and return all the factors basically of the form y minus some polynomial of x. So among those polynomials, I mean among linear parts in y of those polynomials, necessarily will be our polynomial. And return all, say, call them t of x, such that R is divisible by y minus t of x. To reduce the list, we will may consider only t of x or small degree. We know that p of x is of degree at most k, so all the remaining t of x may be just deleted from our list. So this is our plan. And to realize this plan, I need first to explain what means a root, multiplicity of a root in the case of multivariate polynomials. Let's start with that. So how we define multiplicity? So for one variable, this is, I mean, quite known a notion. We say that A, say, is a root of, say, t of x of multiplicity I, if p of t of x may be represented by x minus a to the power of I times such other polynomial, say q of x. In other words, if t of x is divisible in the ring of polynomials by x minus I, x minus a to the power of I. And recall that we live now in the ring of polynomials over a finite field of Q. So do not forget that. And that's why we avoid using the notion of derivative. For real valued polynomial, we also can define multiplicity using derivatives, but we want now to avoid any such definitions. So luckily, we have the definition without any mentioning of a derivative. And this is actually equivalent to saying that t of x plus a has no monomials of degree less than I. Indeed, if we substitute here x plus a for x, we will obtain here x to the power of a times some polynomial of x, q of x plus a. And we see that we obtain here x to the I times some polynomial. That means that all the monomials are divisible by x to the I. And that means actually that this is equivalent to saying that the degree of all monomials is at least I. And the other way around, if we have this property, then we can substitute back x minus a for x and obtain that t of x is represented as x minus a to the I times some polynomial. So, and this second equivalent definition of multiplicity can be used for multivariate polynomial. So actually we need only polynomials in two variables. So let's write for simplicity definition for that case. So we say that a pair of elements from our field, that means from FQ, is a root of R of XY of multiplicity we say I if the following holds. If we substitute x plus a for the first variable for x and y plus b for y, we obtain a polynomial of xy which has no monomials of degree less than I. For real valued polynomial, this may be defined also using partial derivative of degree of order less than I, but we want to avoid such a definition because our polynomials are not real values. Here is an example. Say x cubed y squared plus x y to the 4. This polynomial has certainly the root 0, 0. And that root has multiplicity 5 because so 0, 0 is a root of multiplicity. Multiplicity 5, because this polynomial has no terms of degree less than 5. On the other hand, if we say consider 1, 0, then this is also a root, but this time the multiplicity is smaller. Let's see what is now the multiplicity. So we substitute here x plus 1 for x. We obtain x plus 1 cubed and y for y, so y squared plus x plus 1 times y. And then we see that this monomial has a term y which is y plus something. So which is not cancelled with anything. So all the monomials from this product have degree at least 2. So from this contributes x, y plus y. And so we obtain y plus some polynomial of degree 2. Now, some sum of monomials where the smallest degree is 2. So we see that we obtain a monomial having y, and that means that multiplicity of that root is just 1. So multiplicity 1. On the other hand, 0, 1 has multiplicity 2. Let's see why is this. So if instead of that we take 0, 1, then we will have the monomial x cubed y plus 1 squared plus what? X times y plus 1 to the 4th. And now we see that this monomial has no, this polynomial has no terms of degree 0, no constant terms, and also no linear terms. Is it true or not? No, it seems that it also has a linear term x plus something. So sorry, this root has also degree, multiplicity 1. Bad example. Okay, anyway, so this is a definition of multiplicity of a root of two-variable polynomial. And also we will need a lemma saying that if AB is a root of multiplicity Ci, and P of A is equal to B, that means that the pair AB lies on the graph of a polynomial P, then the polynomial, how we call the polynomial, say R of xy. And P of A, so P is univariate polynomial such that P of A is B, and AB is the root of about the two-variate polynomial R of xy. And then A is a root of univariate polynomial R of x, P of x, of multiplicity also I. So if R has a 0, which is lies on the graph of P, then after substitution P for y in R, that pair AB becomes a root of the same multiplicity. And this is proved just by mere substituting. So to find the multiplicity of that root, we need to substitute x plus a in our polynomial for x. So we obtain r of x plus a, and p of x plus a. And we need to prove that this polynomial of x has no monomials of small degree, smaller than r. And first we use the property that P of A equals to B. That means that if we substitute here 0 for x, we obtain B. So that polynomial may be expressed as B plus some polynomial without a constant term. That means that this may be rewritten as R of x plus A, B, plus some polynomial without a constant term. Denote them it by, say, x times q of x. And now we know that R of x, A plus something and B plus something has no small terms. So, and now in this polynomial, we substitute x for the first variable and x times q of x for the second variable. But because x times q of x is divisible by x, we will obtain in all the degree of all terms we obtain is at least I. So this polynomial has no monomials of degree less than I. No, this can be rewritten using formulas. We know that by definition that A B is a root of large multiplicity. We know that R of x plus A and y plus B is some polynomial t of xi with no terms of small degree. Then we, using this t, we can rewrite this expression, saying that this is t of x and x times q of x. So that means that we essentially substitute x and x q of x in all the terms of t. But it's clear that that substitution doesn't decrease the degree. So degree gets larger. And that completes the proof. Are there any questions about the proof of the lemma? Okay, then we can continue. So let's recall that was our first step in our plan. Find a polynomial of small degree such that all pairs lying on the graph of the given function are roots of that polynomial of large multiplicity. First of all, I will specify what means small degree. We will, when counting degree, we'll consider y as more important variables. So the degree of monomial y, just y, will be equal to k. So the degree of monomial xi times y to the x to the I times y to the j will be obtained as the sum of I and j multiplied by k. And to distinguish this from the normal degree, we will call it k degree. So I will need one new definition of k degree. So the definition is the following. So k degree of monomial, say, xi times y to the j is equal to I plus j times k. And the reasons for this definition will be the following. If we consider some polynomial R, and then substitute P of X for Y, then the normal degree of the resulting polynomial R of X P of X is at most the k degree of the initial polynomial. And that's because the degree of P is k, or at most k. And so when we substitute P of X for Y, the degree of monomials of P of X gets multiplied by k, by j, sorry. And that's the motivation of the definition. And so, first of all, we need to prove that we need somehow to prove some lemma stating that under certain conditions, on the multiplicity and k degree, we have such a polynomial, so of small k degree, such that all given pairs are its root of large multiplicity. So let's state it, this lemma. Let's denote the desired k degree by A. And the assumption will be that A squared over 2k is at least n. N, capital N, is the multiplicity. And now we multiply n by n plus 1 over 2. So more or less we considered the square for multiplicity. And we multiply it by the number of points, little n. So, and this is our assumption. So we assume that the square of the degree is large enough compared to the multiplicity and the number of points. And under this assumption, there is a non-zero R. R is a polynomial of two variables, X and Y. Of k degree less than A, such that, and R is non-zero, of course, R is non-zero, otherwise this is trivial, and such that all pairs xi p tilde p of xi, all pairs on the graph of the given function are roots of R. Of multiplicity. At least capital N. So we need large multiplicity, so we just care that it is at least something, at least capital N. So once again, N capital N denotes the desired multiplicity. Little n denotes the number of pairs, which will be the root. And A denotes the k degree of the polynomial we obtain R. And the proof of this lemma is based on the linear algebra. The constraint that each of our points is a root of large multiplicity can be expressed as a linear homogeneous equality where the unknowns are the coefficients of R. So we need, first of all, find out how many coefficients we have of R. So the coefficients of R the unknowns of R are into one-to-one correspondence with monomials of R, which are allowed in R. And for R, we have the requirement that its k degree is less than A. So the number of coefficients of R that is the number of our variables in our system, is equal to the number of monomials of degree of k degree what is less than A. So we want that the k degree is strictly less than A. And this is actually equal to the number of solutions, to the following linear inequality. So we need to count how many ij, I mean I and j are natural numbers, are there such that I plus j times k is strictly less than A. And this can be represented by the following picture. Let's say that our horizontal axis is j and our vertical axis is A. And we count all the points on the grid that are inside the triangle, right triangle, whose one leg is A and whose other leg is, so this is A over K, the length of one leg is A over K, or the other way around, J is at most A over K, and Y is at most A. So we need to count how many pairs of natural numbers lie strictly before this line, the hypotenuse of right triangles. So the area of the triangle is equal to 1/2 of the product of the legs, which is 1/2 of A squared over K. So we just need to understand that the number of pairs lying below this line, the leg, is strictly less than the square, the area of this triangle. And this is sort of obvious because for every pair which is strictly below that line, we can consider the square, the unit square, whose bottom left corner is that pair. And those squares must cover the whole triangle. I mean, it's interior. Because if something is not covered, for example, if this rectangle was outside our covering, then we would obtain a contradiction. Its bottom left corner then should be strictly below that line. So altogether, all our triangle, all our squares, unit squares, should cover the triangle. And because there is impossible that the covering is exact, because this line has a slope, we obtain strict inequality. So the number of pairs below the line, below the hypotenuse, is strictly larger, strictly larger than the square, than the area of the triangle, which shows that the number of such pairs is strictly larger than a squared over 2 times k. So in our system, I mean, we have larger than a square root a squared over 2k variables. And now we need to understand that each constraint about vanishing of R with large multiplicity in each such pair is a constraint, can be represented by n, capital N times n plus 1 over 2 linear homogeneous equations. So why is this? So for each, we need to understand that for each I, we have n times n plus 1 over 2 linear inequalities. And why is this? If we substitute x plus, say, a, y plus b, in our case, a is some xi and b is the value of our function till the b, till the p in xy. And but now it matters only that these are some constant. If we substitute it and we write this polynomial as the sum of monomials, that each coefficient for which particular xi, yj is a linear function of the coefficients of R. And so for each ij, where the k degree of ij, normal degree is at most capital N, we have one constraint, one linear inequality, this is 0. But certainly the number of, so this n times n plus 1 over 2 is the number of monomial of normal degree less than n. For instance, if n is 1, then the number of monomial of degree less than 1 is only 1. This is constant. Because we have only constant term. And so for 1, this evaluates to 1. If n is 2, then we have to count the number of monomials of degree less than 2, and there are 3 of them, 1, x, and y. And so we obtain indeed 3, n 2 times 2 plus 1 over 2, and so on. So for each I, we need to write a constraint that the coefficient of this polynomial with the term xi, yj, where the sum of I and j is less than n, is 0. And we have n times n plus 1 over 2 such monomials. So in total, we obtain a system. We obtain a system of n times n plus 1 over 2 linear homogeneous equations, and the number of variables is larger than a squared over 2k variables. And our assumption guarantees that this number is at least this number. So hence the number of variables is larger than the number of equations, strictly larger. And the linear algebra teaches us that in that case, the system has at least one non-zero solution. And so this is just the statement of the lemma, that if this inequality is true, then our system here has a non-zero solution. And that completes the proof of our main lemma, called lemma 1. Okay, any questions about the proof of lemma 1? Так, давайте так перерыв сделаем небольшой на 5 минут. Еще половину второго продолжим. kilogram. Okay, let's resume the lecture. So now we can proceed to the second step. So we are given that, first of all, we need to choose capital N, but let's postpone the choice of capital N. More or less, the larger N is, the better. Assume now that, sorry, so on the first step, we will choose some A and also some N, satisfying this inequality. And then we will find such an R satisfying lemma 1, which is non-zero, just by solving a system of linear homogeneous equation. So on step 1, we find R. So on the step 2, we want to adjust our parameters A and N so that if P is close to tilde P, so the number of errors is small, then the polynomial R, in which we substitute P of X for Y, is actually 0. And that will follow from the fact that the degree of this polynomial is small. And on the other hand, it has many roots counted with multiplicities. And this is based on our lemma, I mean, call it lemma 0. So if AB is a root of R of xy with multiplicity I, and P of A equals to B, then A is the root of this polynomial of large multiplicity. So that means that for every point xi where the value of tilde P is correct, that xi is the root of R of x P of X of large multiplicity. So let's write it down. So if P of xi tilde P of xi equals to P of xi then xi is a root of R of X P of X, and the multiplicity of that root is at least capital L. at least capital N. And therefore, the number of roots of that polynomial is at least n, capital N, times the number of i's such that the value of tilde p in xi is correct, is equal to p of xi. And if this large is larger than a, then we will obtain that this is indeed 0. So we need to adjust the parameters in the following way. We need adjusting we need that this number is larger than the k degree. That means at least a and n and the number times the number of I such that p of xi is equal to tilde p of xi be at least a. And so we can choose actually any n, and as a, we need to choose a number so that this inequality is true. Well, let's just choose the minimal possible number. So that means that a is the square root, more or less, of the product n squared and n and k. So let's choose a equal to the square root of n plus 1 times n times k. Then this guarantees that such R exists, and so step 1 will can be successfully finished. And then we also need this. And to this end, we need that the number, call it, say, u. We need just that u is at least a over n. That means approximately n plus 1 over n times nk. So, and that explains the formulation of the theorem. We have said that if the number of errors is at most n minus approximately square root of nk, then something good happens. And now we see that the larger is n, the better, because n plus 1 over n tends to 1. So let's choose, say, n equal to capital N equal to little n. Then this will be equal to square root of 1 plus 1 over n, which is close to 1 times square root of nk. So this is our choice of parameters. Choose, say, capital N equal to n, then choose a by this formula. So a is about n times square root of nk. And then we will have that if the number of correct values in the function tilde p is at least about square root of 1k, then our polynomial has the property that it has many roots. So counting with multiplicity, the number of roots is larger than its normal degree. And so we obtain lemma 2. So if the distance between p and tilde p is at most n minus our u, that is approximately n minus square root of nk. To be more precise, we need to take this one and to round it somehow. Then the number of roots of the polynomial r of x, p of x is larger than its degree, and we count roots counting polynomials, and so that polynomial is just a zero polynomial. So on the step 2, we have proved that if the number of errors is small, then if we substitute in our polynomial r p of x for y, we obtain just a zero polynomial. And then we can just proceed to solve, to step 3, say, and use Bezout theorem. If we know that r of x, p of x is 0, then this is actually the same as saying that r is divisible by y minus p of x. So in the case when of the ring where of polynomials in one variable, this is just normal Bezout theorem. And now instead of just say normal numbers, we have polynomials. So r of xy can be considered as a polynomial of y whose coefficients are polynomial in x. And this inequality says that p of x is the root of the polynomial if and only if r is divisible by a linear polynomial y minus that root. And the proof in one direction is trivial if, I mean, from the right to the left, because if r is divisible by this polynomial, then we can just substitute p of x for y and see that r vanishes when we substitute p of x for y. And in the other direction is just proved as Bezout theorem. We just divide that polynomial using the long division algorithm by a linear polynomial p of x. And after the division, we will obtain some quotient, say q of yx, and some remainder, say t of x. And the degree of the remainder is less than the degree of divisor. That means that the remainder is a constant polynomial. In other words, this is polynomial without y, so polynomial only of t of x. And so we can represent our polynomial r as y minus p of x times the quotient times q plus the remainder t. And then we just plug p of x for y in both sides, in the polynomials in both sides. And we see that the right-hand side becomes t of x, and the left-hand side becomes 0, just by our assumption that r of x, p of x is 0. And so t of x is a 0 polynomial. So that means that r is divisible indeed by y minus p of x. And so on the last step, we factor r. So we represent r in the form of the product of irreducible polynomials. Say R1 or Rm. So these are irreducible. And just look at all of all those polynomials which are linear polynomials in y. And every such polynomial may be represented as y minus something. And for all such polynomials, we obtain one entry in the list. And we know that our polynomial is in the list because we know that r is divisible by y minus p of x. So our list contains our polynomial, and the number of the size of the list is equal to is at most the degree of r in y. And this degree is at most the k degree over k. So this is at most a over k. And let's see what is the size of a. A is approximately equal to the square root of n cubed k. So a is approximately equal to the square root of n cubed times k. That means that a over k is approximately equal to n square root of n over k. Well, that was promised, that the size of list is n times, approximately n times the square root of n over k. And so I skip one part of the proof is skipped. That is the algorithm to find this factorization. So this is beyond our reach, actually. This is a very complicated algorithm. So we just use the fact that such a polynomial time algorithm exists. And this completes the proof. Так, есть вопрос по доказательству? Так, ну хорошо, сейчас я дам последний тест. На этом все наши лекции закончатся. Оценки вы можете в таблице увидеть. Так. что я... Так, значит, у вас больше, чем обычно, до 14:05 можете сдавать. Значит, я не знаю, как я оценки донесу до учебной части. Но, скорее всего, кто-нибудь зайдет в учебную часть и поставит оценки тем, кто... Ну, оценки в смысле зачет, тем, кто их заработал.